Dear students, we are going to discuss about underground blast design today in our this lecture session. Why the blast design is needed? You know that the rock needs breaking from the breaking and dislodgement from the in situ place. In situ means as it is naturally found in massive form, the rock is or the ore is formed in massive form in its original occurrence place in the earth, inside the earth is called in situ occurrence of the rock. Now, the rock may be overburden also, the rock may be waste rock also, the rock may be ore also. Necessarily in case of ore and overburden excavation and its loading, we need the rocks from in situ in the blasted forms, so that it is smaller to handle by the loader or by the human being to load into the tubs. So, it needs blasting, and blasting needs a design. Why? It needs a design so that the fragmentation takes well, the fragmentation of the rock takes properly. What is the proper fragmentation? What is an ideal fragmentation? Suppose if we break 1000 tons of ore in blasting in open cast mining, or say 100 tons of ore in underground mining after blast, say 100 tons of ore in underground mining. So, the boulder size which is having the dimension, the largest dimension more than the 0.8 times of the upper gap of the primary crusher, that means acceptability of the primary crusher where the crushing takes place for the minerals and coal. So, that acceptability, that acceptable boulder, what is acceptable boulder to the crusher? Upper gap into 0.8 times, that means suppose upper gap is suppose 1000 mm, say 1 meter. So, the maximum dimension of the boulder acceptable into the primary crusher is 800 mm only, 1000 millimeter and 1 meter. Suppose 1000 millimeter or 1 meter is the upper gap of the primary crusher. Gap means the upper gap, you can say GAP gap, but gap is the mineral dressing word, mineral processing word. So, I have used that here. So, if the upper gap is 1000 mm, so the boulder size going into that should not be exceeding in any of its dimension, 3 dimension more than 800 mm, meaning is that. So, that is the acceptable boulder. Now, all the suppose I have blasted 100 tons of material. So, out of 100 tons of material 98 tons should be acceptable to the primary crusher, only 2 tons should not be acceptable to the primary crusher boulder size, that is called the ideal blast. Earlier there used to be the concept of 5%, this slackness given to define this proper blast, but nowadays the degree of acceptability is only 2% oversized boulders. We should have a heaped up throw. The throw should not be very thin and thrown like a big throw given over a big range and the material is spread all along the floor of the mining phase. That should not happen. It should be heaped up properly as shown in the previous diagram. You must have seen what is heaped up. Optimum consumption of explosives. Why it is required? If we use more explosive, there will be more dust and more finer material which will be not required, because I also need some of the product which is called lump ore, okay. And also I need fines. Fines is generated automatically due to blast, but lump ore is needed in production to eliminate the cost of agglomeration of ore or coal, which is required extra in case of fines product. Fines products are inevitable and lump products are with great difficulty it is achieved to the size range as required by the customer. So, the blasting has to be very effective so far as dislodgement throw is concerned, should not be excessive throw, should not be slabbing of the mining face, only the blast has taken place, particularly it happens in surface mining. The blasted portion remains attached to the mining face, it is not thrown out because of less explosive used. Sometimes less explosive used is causing big boulders generated, which will not go in the crusher, and there will be lot of extra cost coming in secondary blasting of the boulders. To avoid such thing, to have neither too much of throw nor too less of fragmentation degree of fragmentation, adequate degree of fragmentation on the mining face. In other the cases, we need a optimum use of the explosive to achieve the best powder factor. What is powder factor? Ore blasted ideally in tons or cubic meter, whatever you say, per kg of explosive use, that is the powder factor. So, we should have the optimum use of explosive. It may be surprising to all of you that drilling and blasting is the one of the major chunk of the cost incurring in the total operating cost, maybe around 20%. Okay. Depending upon the various situations, it ranges from 15 to 18% on an average, but maybe even 20%, 21% also sometimes very high. So, this cost of the drilling and blasting should be least. From that point of view, we should have the optimum usage of explosives. So, the blast design is required. Now, least ground vibration. In open cast mining, there are villages around, there are inhabited places around the mining area, and that is suffering a lot because of ground vibration because the scale of blasting is high, bigger, and more explosive is used. If the explosive used is not getting consumed inside the ground properly to have the most best fragmentation and with the best tonnage yielded with best powder factor, the effectivity of the blast is lost, and the extra energy, the energy which should have been used for the better fragmentation and the better throw and the energy should have been used for better fragmentation and better throw, and also not the projectiles going much away into the village areas beyond the safety zone, it should not fly off. So, from these all points of view and the least ground vibration, you should impart the least ground vibration to the surrounding inhabited area. So, how to use the explosive, with which kind of hole parameters, that is of utmost importance in surface mining. Also in underground mining, the ground vibration, least ground vibration is desirable because more the ground vibration, more the disturbance to the strata, and the roof will be becoming weak, may be needing the more of supporting costs and expenses. So, to reduce that, we should have the least ground vibration. The most of the explosive energy must be used for best fragmentation and the quantity which is required. This is the best heaped up material, and if the material is thrown out much more away, then you will find that the height of contact of the heap, which is shown 1.8 meters above the floor level, will be coming down, maybe it may be 1.2 meters, 1 meters, and the material thrown out much thinner on the floor side. So, that thinner material needs to be dosed to the blasted face with the help of machineries, which will be extra time taking, and the production process to start with will become delayed. So, that is not desirable. Factors to be considered for blast design: depth of the hole, distance between mouth of the blast hole on the face to end of the hole inside the ore body, it is called the depth, depends upon productivity required. In one blast, how much tonnage of material is required, it depends upon that. In underground mining also, the manual drilling makes 1.2 meter of drilling, 1.5 meter of drilling. In fact, they use 1.5 meter of rod, and with drifters it may go up to with drifters it may go up to even 2.5 meters on the drifting face, and in case of sub-level stoping, and in case of thick seam mining where sub-level caving is done, there the fan patterns are being drilled around the periphery of the drive edge. I will show the diagram. So, those holes are quite big, that may go even 40 meters deep. Now, what is burden? Distance between just a minute, spacing is coming in between. Spacing is a distance between two consecutive holes in the same row. I will show you the diagram later. Burden, distance between two adjacent rows of the holes, two nearest rows of the holes, which are blasted with a different time sequence, with a different instant of time, by giving a time sequence in between, by having a delay detonators in between. So, diameter of holes are what? Normally 25 mm in case of manual drilling, and I said the drifter drillings, it is normally 35 mm, and it goes as high as up to 150 mm even, and the depth goes up to 40 meters, whereas in case of manual drilling it maximum goes up to 2.1 meters by giving extension rod with jackhammers. So, from 1.5, 1.8 rods are there, next is 2.1 meter rod is there with jackhammers. Jackhammer diameter is hardly 25 mm maximum. So, that I mean to say the handheld jackhammers. The volume blasted ore is what? The N has moved away, N is on the top of the sigma head, and at the bottom N is equal. So, that is basically the depth of hole into spacing into burden. So, this is the summation of volume yielded by each hole on the mining face basically. Rock strength, the design parameters are depending on this rock strength also. Compressive and tensile strengths are responsible for fragmentation of rock due to blasting. You must have heard the P wave and S wave etc. in shock waves etc. So, that is creating tensile force after the shock wave returns from the free face, and that is causing the tensile force, that tensile force is causing the fragmentation of rock. So, the tensile strength is also important. Of course, compressive is important, while because the rock is getting also compressed by the two sides of shock waves moving in opposite direction after getting reflected from the free face. So, both compressive as well as the tensile forces are being encountered by the shock waves to break it. So, this tensile and compressive strengths are quite useful to decide about how much strength of explosive should be used, what strength of explosive should be used for blasting. Required productivity, how much requirement of productivity is that decides the depth of hole particularly, and also the fragmentation level, nearness of the human working area. If it is there nearby, then least ground vibration is required in mining underground also. Free face required. See, the design, the main onus of designing the blast pattern is lying on a fact that free face provides a better fragmentation level. Why? The wave moves from the hole after blast, the shock wave moves after the blast from the hole to the free face side, and because there is a change in the density of media after that air starts after the free face, the sound wave, the shock wave gets reflected, and the reflected wave, there is a conflict between the reflected wave and onward moving wave from the hole to the free face side. So, that is creating tensile force. It is initially creating compressive force, and after that it is when passing each other the waves, the wave on one wave is moving from hole to free face, another wave, another part of the wave already has moved to the free face and has got reflected. So, when it is crushing the ore, the compressive strength is getting encountered of the rock. When it is passing by overlapping each other in opposite direction, then here the tensile force is created. So, that breaks the rock. So, free face is a must for better dislodgement and better fragmentation. So, the design has to be made in such a way that in the first initial row blast a free face should be developed, or else in the past the free face was being developed before the blasting by undercutting the drift face, particularly in coal mines where the coal drift was being encountered. So, by coal cutting machine, but that practice has become redundant these days, it has become obsolete. Coal cutting machines have also become obsolete, but I will show that machine in diagram in next few slides. Blast designs for drivages and roads. See, cross section of drivages are rectangular. The mining face is having all 4 sides closed with unblasted rock, which means no free face. But for good fragmentation, free face needs to be created with the first row blast at the center of the face. Then next outer rows are blasted, differing the timing by providing delayed detonators in between by at least 25 milliseconds. Most commonly 25 to 50 millisecond detonators are used for better fragmentation effect. Free face has to be developed much in advance than the next round blasts. Okay. In view of the above factors, a few blast hole designs are shown in the next slides. See, you can see this is a mining face where the drift is getting moved ahead. So, you can see the central black spotted holes are having dotted line inside inward, centrally inward, concentrically inward. So, that shows the direction of the skewing of the hole while drilling. It is getting well where the first center hole is horizontal, after that next periphery of the hole is there are 6 holes on the next periphery. So, that is the first round along with center. So, that is blasted first to make a cone shaped these holes are concentric. So, when it is blasted the cone comes out first to provide a free face from the center of the cone. A free face is then the next round is also made concentric. You can see the plan shown at the bottom view in the bottom of the view. That is called pyramid cut or cone cut. It makes a cone shape. Okay. Cone means circular and then cone pointed towards the central hole. So, the second row is also blasted in the second round by giving delay element. Then the third row is, you can say there are third row of holes which are drilled either horizontally or outwardly. The extreme holes nearest to the edge of the drifting face where the hatch line has been shown, there the holes are drilled outward little. Outward means like this. It is not centered towards that, it is outward toward the edge of the drifting face. Okay. So, why it is done? So that we will have after blast the smoother face, smoother floor and smoother sides. It will take care of the tougher zone which is having support from sides also. There is no free face. So, this is the wedge cut or pyramid cut. So, this is the cone cut or pyramid cut. Now, on right hand side the wedge pattern has been shown. Earlier what was happening in case of cone cut, there was a single point and all the holes were getting drilled towards that in the first row of holes. After that second row of holes also little skewed, maybe becoming concentric at the greater depth, imaginary depth. It is not the real existing depth of the hole, but it is the imaginary depth. And the third round has been shown outward. See, you can see in the plan, it has been shown outward toward the edges of the cross section of the road or the drift made or the drivages being made. Now, in case of wedge cut, what is happening? There is no cone shape, it is a wedge shape. Wedge is like this, this is the wedge. So, this is this shape. So, fingers can be viewed, the fingers can be viewed as a whole. See, if this is the view you are looking at, then the fingers are running horizontal, the drills are running horizontal, the holes are running horizontal, and it is forming a wedge. Okay. It is wedge towards you if it is shown. So, if I view it from my side, it will be like this, the holes will be like this, and the holes will be mining face is like this, the mining face is like this and holes are like this. Okay. So, it is a wedge, it is a planar, two planes are coming to form a wedge. Similarly, outer holes are also made horizontally, but in wedge shape. Okay. And of course, the third row of the holes seen just adjacent to the edge of the drift or the drive edges cross section is again outwardly made, it is made outwardly, it is made outwardly like this, it is not wedged like this. Okay. So, this is the wedge cut, this is not a cone cut. Pattern of drilling holes in drive edges by jackhammer, it is a fan or drag cut. Why it is called drag cut? You can see the bottom black holes, black spotted holes are drilled downward, and that is made the first round, that is first blasted in the sequence, that is first blasted in the round, that is the first sequence to be blasted, the black portion of the hole going downward. It is looking like fan if you view it from the side, it is the side view or end view or whatever you said. So, this is a drag cut. The positive shown cuts are adjacent to the face. So, it is upward, even the side holes are like this towards the edge of the drive edges. So, that smoother sides and floor and the roof and floor are available. Okay. So, that is why it is put downward, the black hole is put downward, see it has gone downward. So, that is first cut, the bottom portion is first cut, that is cut by giving the first blast direct without any delay. Then upper holes which are shown as hollow holes, the hollow small circles, that is the next round after the bottom portion has blown and made a free face has been made. So, the next round is blasted and next round is blasted. So, development of the free face goes on like this, and the dislodgement takes place to give a better fragmentation. These are the holes for bigger drive edge cross section. You can see here it is quite big, section 4.2 meters wide, and there are it is the sequences are shown by 1, 2, 3, 4 written in Roman notations. Okay. So, these are the sequences followed, and this is basically pattern of drilling holes in drive edge by jackhammer. It is given by fan cut. See 1.8 meter is the maximum depth, okay, of the cut of the blast. See the the first hole or the first the first row of the holes which was black spotted are called sumpers. The holes, that type of holes are called sumpers or cut holes. Then the hollow holes are the easers, that eases away the next blast in sequence. Okay. Then the last one is nearer to the mining, that drift face at the corners, where the trimmers that goes up at the end to give a smoother edge. So, this is the pattern of blast. Various drilling patterns, in fact, in fan cut, the cut holes are fired first naturally. The cut holes which were, go to the previous slide, again previous slide. Yeah, you can see the cut holes are at the bottom. So, that is made first blasted in the sequence. So, that the free face is provided and rest of the material while taking blast in the upper rows like this, due to gravity also it will be falling and giving a better fragmentation because of free face at the bottom. There is a hollow place after free face. So, the remaining holes, the delays used are indicated by 0, 1, 2, 3, 4 etc. The remaining holes are fired next with the delays indicated by 0, 1, 2, 3, that is in the previous slide, just previous to this, and 4 below are below the hole positions. This is another pattern shown, again it is the either the cone cut or the wedge cut etc., but on larger face, and the firing sequence have been shown by different 1, 2, 3, 4 whatever sequences have been allotted to the different rows. Next please, here also spacing burden are shown, you can have a look what is spacing and what is burden. Anyhow, next, this is the coal cutting machine operating on the drivage face, and it is undercutting machine basically. There is an free face cut, undercut on the right hand side, on the side view it has been shown as the undercut. So, and the drilled portion has been shown in upper part of the mining face already, which is integral part from the roof side. So, the block is supported from all three sides except from the bottom side where undercut has been given. So, when the blasting takes place, the bottommost row of the hole is first blasted as the cut holes are there at the bottom, that gives further free face to the upper holes of and then it gets blasted properly with better fragmentation. Next please. This is the coal cutting machine. It is out of date these days, very rarely it is being used, maybe in some old mines. So, there is a jib in the front, that jib is having a rotating chain, a creeping chain. So, that when brought, that is when brought in contact with the bottom of the coal face, it goes on cutting. When the chain moves, when the chain with the picks, cutting picks moves on the jib, on the periphery of the jib, it goes on cutting the coal to provide an undercut. Next please. Fan pattern deep hole blasting. What is deep hole blasting as per DGMS rule? Any hole which is more than 3 meters in depth and having 50 meters and having, not or, and having 50 millimeter diameter, as per the definition of the deep holes given by the DGMS, any hole which is exceeding 3 meters of depth is called the deep hole, and normally according to the depth the diameter reaches 50 mm by its thumb rule. So, the holes which are going beyond 3 meters are normally more than either 50 mm diameter or more than that. So, this is used for in case of sub level caving, in case of thick seam mining or special mining methods in coal mining, and also sub level caving used in case of metal mining stoping methods. So, I will show you the diagram how it is done next. It is done by drifter. The 40 meters hole cannot be made by manpower, it is made by a drifter machine which looks like this. It has got a drill machine on the roof, it is rock bolting done with a sheet, so that with a protective polymer sheet, strong polymer sheet which will not allow any small chunk of material to fall onto the machine and damage it or to injure the operator sitting just below the canopy shown at the central part of the machine, and it is drifting like this. The boom can be lowered or given a complete coverage by the boom. By the boom like this it happens on a plane, it can move and then it can drill also. It moves like this. Suppose this is a mining face. So, it moves like this and it can drill on the periphery or anywhere in between. Okay. So, that is the way it is functioning. Next please. Now, we have come to the stoping area of the metal mines. You can see the different drivages. This is the drift. The drifts are having the ore collecting passages as shown by the loader and the different trucks moving out of the chutes. Small holes are shown at the bottom portion of the light blue part of the face. Okay. This is just a section shown. Now, the drift in the upper in between the upper part of the drift made in the upper part of drift is what? It is in the strike direction, okay. Whereas, the cross cut is along the width of the ore body in parallel to the width of the width direction of the ore body or thickness of the ore body, you can say, and drifts are along the strike direction of the ore body. So, the light blue passages are shown with the openings, that is a drift, and the drill machine is coming along that and drilling in the fan pattern covering the whole width of the body, ore body, and then it is getting blasted. So, this is the fan pattern drilled in the floor side, on the floor side. Now, there is fan pattern also drilled in the on the roof side, that is also there in sub level caving. So, these two, see the bottom drift which is serving the purpose of loading from the small chute shown 4 numbers of cross cuts, and that is connected to the chutes of the stope. From there the metal is being taken out. So, above that is the main drift level, whereas the from where the long holes have been made downward, that is sub level developed to cover the entire height of the ore body in between the two main levels. The another main level on the top is not shown. This is another diagram. In the upper part there is open cast mine seen on the done in the past, and the thick blue line is showing the width of the ore body as indicated by the red letterings and the arrowheads, and the strike direction on the top of the ore body is shown along with the dip direction, and you can see there are multi sub levels made, so many sub levels made on the light blue side of the ore body. It is just a section shown. So, that is connected to the drift. You can see on the top of the white patch going inclined on the extreme right hand bottom side, there are 4 passages cross cuts made into the ore body. Cross cuts are made, that is a drivage running in parallel to the width of the ore body. That is a drivage in parallel to the width body. It is going like this, and whereas a drivage is going like this, a drift is going like this, that is in parallel to the strike direction. So, that is a drift that is getting connected to the main level at the bottom, and whatever in between is coming, whatever the light blue lines are shown horizontally along the width of the ore body, that is the cross cut made, but that is also forming the part of the working level, and that is called sub level in between the main drifts. Main drifts are shown at the bottom with where the yellow transfer system has been shown, haulage system has been shown. There will be similar level above that which has been not shown. You can see the different holes on the lighter side of the ore body. So, in between, see this is in staggered pattern, the holes are in staggered pattern, just see one on the top and staggered at the bottom like this. Next please. So, what is fan pattern? You know, after the blasting of the upper row of the sub level, the black portion ore is coming onto the chute and it is getting drained out. The rectangular bottom portion is showing the chute. It is helping in draining out the material through the cross cut and then connected to the level along the strike. So, that is upper part shown. Now, bottom part is the next in staggered pattern with the previous one. Whatever rectangular part is there, that was the previous drivage, that was the previous cross cut section. After blasting it has happened so, it is no more open drivage. Bottom portion is staggered with that, the two another drivages are staggered and the holes are made upward side by the drill machine, and these holes are filled up with explosive with a special kind of machine which is called charging machine, explosive charging machine in upper side, otherwise explosive will fall due to gravity. So, the stemming is also done by plugging the, maybe these days air plugs are coming in very strong plastic polythene packs, or some cushioning materials are coming which is pushed by the machine into the holes, and then blasting is taking place of the entire fan. The whole material falls, and then again the whatever the opening has been shown at the bottom, that becomes the draining passage for ore to come out to connect with the level. So, this is the pattern of blasting, long hole drilling blasting. Specifications are given on right hand side, it can be read properly. So, and dimensions are also very clear, it can be understood well. Blast patterns for manual stooping, depleting, longwall coal mining. See, I have just explained here, actually I will show the diagram to you. Next please. See, in this the top is the roof, bottom is the floor. In between that there is a central line. If the height of the face is 3 meters, then at 1.5 meters there is a central line. Now, on above the central line, just above the central line and just below the central line, there is a one row of the hole, that is drilled wedge like this, it is wedged like this. Earlier there was a vertical wedge, now it is a parallel wedge. Okay. It is running like this, the holes are running like this from both the upper and lower side and forming a wedge to cover the entire length of the mining face. Then upper row is also slightly made skewed towards wedging. Third row on the top is wedged, I mean to say it is made skewed towards the roof side, and the floor side also similarly bottom holes. So that I will get the smoother floor and a smoother roof. So, it is covering the whole width of the mining face for production purpose, whether it is depleting face or it is a long wall face if required by manual system or semi mechanized system instead of shearer method, then these patterns of holes are used. Similarly, in manual stopping methods in metal mines, these kind of patterns are used. Now, we will come to the shaft sinking. You can see at the it is again the cone pattern. The central part is forming cone to blow off first in the first sequence of blast. Then next little wedged, you can see the shaft section and at the bottom, and you can see the wedging part, and then little the next periphery of the hole is little skewed inward, and third one is most outward. So, that smoother section of the shaft is obtained. Next please. This is halfway of drilling pattern. The vertical holes are made to blast in a small benches, half bench. The left side is the blasting, the bench getting prepared for blasting, whereas right side is having already fallen muck due to previous blast. That fallen muck is first removed, and then free face is provided to another half, the white one on the left side along the diameter, vertical diameter shown in the upper section. So, after that when the blast takes place, the free fall again takes place from the, this is a fan pattern used in shaft sinking. Again the half is used for fan making and it is blasted. The free face is at the central line where the dotted line is shown. Correspondingly, the vertical free face has been shown in the bottom section of the shaft, the side view of the shaft, and muck pile is removed on the left side. Then after blast is taken. Next please. Yeah, this is for rectangular shaft, the fan pattern used. So, this is used for rectangular shaft patterns. The advantage of fan pattern is that you can see from the central two lines are skewed along with each other, and the entire lines are skewed with each other. On the left hand side holes are skewing on right hand side, the right hand side holes are skewing on left hand side. So, it is forming a sort of wedge and it is covering very big area, and it is getting blasted to cover the entire area of the rectangular shaft, cross sectional area of the rectangular shaft. In the upper plan view, you can see some of the dotted lines, that is that dotted lines are showing the skewing direction of the holes, the with the small tiny circles. the mouth of the holes are represented by small tiny circles on the surface.